I have to explain to you why I will give the lecture in English. So you see, it's general relativity. It's not allgemeine Relativitätstheorie. I hope it's okay with everybody if I speak English. The reason is that this course addresses two quite different groups of people. The first is master students here at the University of Bremen. I think that's a majority here in the room. But it's also addressed to our new Graduiertenkolleg, research training group or something like that in English. So this is a place where PhD students are educated. And most of them are coming from abroad. And for this reason, they don't understand German. They don't speak German. And since they are expected to participate in this lecture, we have to do it in English. So I hope that's okay with everybody. If you feel uncomfortable with asking questions in English, just ask questions in German, that's okay. Then I translate quickly. This should work. Okay, so this was the first thing I should explain. So the reason that we have this course for two quite different groups of people has another of other consequences. The second consequence is that we have to record it, because not all participants of the Graduiertenkolleg are here in Bremen. Some of them are in Oldenburg, some of them are in Bielefeld. Actually a fairly big group in Bielefeld. I think almost as many as are here in this room. So they also want to participate in this. And because I cannot be in two places simultaneously, we have to do it this way, that we record it. Then it will put online, and everybody can watch the lectures online. I think that's also convenient and helpful for you if you miss a lecture, then you can watch it online. The address where you can find the lectures is the following. So the video recorded lectures will be available at the following address. M lecture. No, without S. M lecture. Unibremen.de. So I don't know how long, I guess maybe with a delay of 24 hours or something like that.
Yeah, even less.
Even less than that, very good. So it will be available there. And then you can watch it again if you have missed something. And it will be available there. You don't need a password, so everybody can watch this if he likes to. You will also get lecture notes, typed lecture notes. I will type them up and then distribute them. For this reason, I need the email address of everybody. I have the email addresses from the people who have registered at StudIP for this course. And I also have it from some other people, but I'm not sure if I have it from everybody. So I give this list now around. Please check if you're on this list, and if you are not, then put your name and your email address in a readable way on this list. Then you will get the lecture notes and also the problem sheets and the solutions to the problem sheets in due course, of course, after we have discussed them. So there will be problem sheets, but I will not mark them. So the way I do it usually is that we just discuss problems together. My hope is that one of you will come to the front, present the solution at the board, and then we discuss them together. And if you want to have an exam for this course, if you want to get credit points for this, if you want to have it as a Wahlpflichtfach, then we will have an oral exam at the end. So just to give me a rough idea, how many of you would be interested to take this exam? 4, 5, 6, 7. Okay, that's not too bad. Yeah, I can manage. Good. So, the oral exam will be the only criterion. Yeah. So there are no points for the worksheets. So we have we will meet 3 times a week. So the times are, I should write English, Wednesday 16 to 80, it's Thursday 12 to 14, and Friday 12 to 14. And we are in this room only today. All the other lectures will be in a different room, and I think in one with a better board. So it will be in 33:10. So this one is occupied today with some other happenings, so a colleague asked me to change room with her. And it was announced in the way that we had the lectures on these 2 dates and the tutorials here. I'm not sure, maybe we should change this. Maybe it's better if we have the lectures here. Then I could hand out the worksheets on Friday, and we could discuss them on the next Wednesday. Then we had 1 week finished after discussing the problem sheets for this week. I think that would be better. Then you have something like 5 days if you are ready to work over the weekend. So I think this should be a reasonable time for looking at the worksheets, trying to solve them. So my suggestion would be that we have the lectures here, and the tutorial here. Yeah? Is that okay with?
Wir haben Freitag von 12 bis 14 Uhr noch eine andere Vorlesung.
How many are this? Wie viel?
Alle Physik-Master. Freitag die Experimentalphysik-Pflichtveranstaltung.
Okay, so then we have to change this. Yeah, that's obvious. Yeah, so we cannot do the Friday slot. It's very difficult to get rooms here, so I have to see what we can do. So should we just how do we do this? Should I write a schedule on the board and then we check which days are possible, or has anybody a suggestion where you think that this should be a convenient date? Or should we go through the whole schedule? Okay, I think then we have to. So it's only about the Friday. Nur der Freitagtermin ist problematisch, oder? Nein.
Aber donnerstags wird es auch gehen, wenn wir da die Übung machen, dann würden wir nicht erst mal zur Übung gehen.
Mhm.
Also für mich wäre das okay.
Ja, das sind Donnerstag und Seminar sind nicht so wichtig.
Mhm.
Wo man einmal da sein.
So please raise your hand. How many of you could not come Friday 12 to 2? Okay, that's all, more than half of you. And how many could not come Thursday 12 to 2? 3, 4. Yeah, it's also quite a lot. So maybe you should try to get other dates for both. A possibility would be, because there's really a room problem here. So it's really difficult to get a lecture room at convenient times. Would you be prepared to come to ZARM? That's the building where the drop tower is. That's the institute where I work. We have seminar rooms, and there's a certain chance that we could find a place there. But I'm a little bit skeptical if it's possible to find a room here in this building if we try to change it. We could try, but maybe we would have to go a little bit farther away if we are ready to this. Okay, then we try to get new dates, and I make a schedule. So the Wednesday is okay. Wednesday 4 to 6 is okay? Good. So this is, Monday, Tuesday, Wednesday, Thursday, Friday. Shall I leave out 8 to 10? So that would be the possibilities. Actually, Monday is very inconvenient for me because I'm usually, quite often, I'm in Berlin on Monday. So shall we check Tuesday at 10? Who could not come Tuesday at 10? That's 2. Tuesday at 12? 1, 2, 3, 4. 2 to 4? 1 and 2? Yeah. Actually, we could also include, why not, 4 to 6. 1, 2, 2. Okay, Wednesday, 10 to 12. 3. Here we are already. No, wait a minute, we are at 4. Wednesday, 12 to 2. 3. Oh, you have a busy schedule. 4 even. 4. 2 to 4. 1, 2, 3, 3. And that's the one we have already. Thursday, 10 to 12. 1, 2. Okay, that's the one which was scheduled originally. Let me just check again how many could not come on this. Drei, vier. 2 to 6, 2 to 4. 1, 2, 2. And 4 to 6. 4 to 6. Thursday, 4 to 6. Excellent. So we have found one. That's a very nice time. I like I like this late hours of the day. Friday, 10 to 12. 2, 3, 3. Okay, that was the one which was scheduled. How many were these? Who could not? This was a lot, right? 1, 2, 3, 4, 5, 6. So we can forget about this. 2 to 4. 2 to 4. 1. Only one. Oh, looks bad for you. And 4 to 6. 1. Also 1. You're hesitating? What? You want to go home early, right? That's no reason. Was that right? 0? Okay. So it's 3 times 4 to 6. Excellent. I like this, really. Is it okay with everybody? Then I find to get rooms for these two. So this would be already tomorrow, right? Let me see. So then we would have and I have to see if I find a room.
Is it possible to start Cine Temple?
Yeah? Would that be okay? To start at 4 sharp? Or then we would finish by 5:30. Every time?
It depends on where the lecture is and how far we are.
Okay, yeah. Okay,
So maybe
that's...
let's try it.
Yeah, well, you need, unless if you are really slow, you need not more than 10 minutes to go to Zaum, for instance, which is exactly on the opposite corner of the campus. Yeah? And will hardly be any room farther away than this. So I think it should be possible to do it in 10 minutes.
Let's try.
Okay. So, yeah, so then I would have to do this quickly, right? Because it's already for tomorrow. So, actually, I have a meeting tomorrow at 4. Oh, sorry. It's only this one day. So then I suggest that we drop this lecture today, that we have only 2 lectures this week. Well, it's not too bad, actually. We wouldn't have a tutorial in the first week anyway. Yeah? So my suggestion is that that we drop this date, and that we have the next lecture Friday at 4, and I try to get a room for this and let you know. Yeah? So is this agreeable to everybody? Good. So I think it will most likely be in Zaum. Yeah, I think it's very likely that we find a room for this time in Zaum, that we have our seminar room available at this time. Would this be a problem for you to come with a camera to Zaum?
I cannot say. I have to check my schedule.
Yeah. It's just about your schedule, or also because...
because I have another lectures also to record, so I have to check it with my office.
Okay. Yeah. Which of this slots should we use for the tutorials?
Tuesday?
Any preference? Tuesday, the one in the middle. That's fine with me. Yeah. So then. So the one which would to be recorded would be these two. So the first one would be Wednesday in this other room here in this building. So this should be okay with you, right? And the other one which would be recorded is the one then in Psalm. Or if this, well, actually, we also have the better board here, so maybe we should do the lecture here, if there's not a strong argument against this. Yeah, should we have the lectures Wednesday and Thursday, and then the tutorials in the relaxed atmosphere in our seminar room at SARM? I think that's a better choice, yeah. But not this week, of course. This week I will do a lecture here. Yeah, I will do a lecture this week. So then we have to check with you if this would be possible for you, if you could come on Friday to SARM. So so sorry for the confusion, but I do my best to to suit everybody. So any more comments or questions about the organization of the course? So then I would hand out the first sheet probably this Friday, but there would probably be material in the sheet which we would get only on Wednesday, because I think I don't get that far in 2 lectures, but I think that's maybe tolerable. Okay. So was this all as far as announcements are concerned, or anything else? Let me check. Yeah, I think that's it. And then we could start with the real thing. So maybe I should, well, I've already mentioned, I should also put it down, typed lecture notes. Will be distributed. But nonetheless, I would strongly recommend also, to look a little bit in books. What's the word? Complementary reading. So I will suggest a few books which I like and which I think would be helpful as complementary reading, not in the sense that I use these. Yeah? I will not proceed along the lines of one particular book, but I think it's always a good idea if you also go to the library, look into the books. So I will recommend 3 books which are of a very general nature, which give a very general introduction into relativity. So in my view, they are as easily readable as a book on general relativity could be. And then I give 3 which are a little bit more advanced, in particular for those of you who are planning to do own research in relativity. So that's mainly the PhD students, but maybe also 1 or 2 of the others might be interested to go a little bit deeper into the subject. So the 3 elementary books are the one by Wolfgang Grindler, It's Just Relativity. Yes, it's Oxford 2001. Wolfgang Grindler is one of the grand old men in relativity. Actually, one of my teachers. I had my first postdoc position in Dallas with Wolfgang Grindler. He was the one who invented the notion of a horizon. I think everybody has heard about event horizons and particle horizons, and that they play an important role in relativity. And he was a person who invented this notion in his PhD thesis in '56, I think, who is now a fairly old man. I think he's close to 90 now. And he is didactically very good. So he has written a couple of textbooks. That's the most recent one on relativity he has written, and I think it's very, very nicely readable. So it certainly puts an emphasis on physical understanding, as opposed to the mathematical formalism. So he keeps the formalism as low as possible. Of course, you need some sort of mathematical formalism if you want to do relativity, but he is not stretching it too far, not more as possible. Another one, which is a typical British textbook, is the one by Houston and Todd. This is called An Introduction to General Relativity. And that's Cambridge, I think. Yes, Cambridge, 1990. Typical British, I said, this means very compact, very concise. Not a single word more than absolutely necessary. There are more formulas than text. So the emphasis is clearly on calculations. So it doesn't explain much. So if you really want to understand what's going on physically, if you want to get a deep understanding of things, then probably you will be disappointed by this book. But if you want to learn doing calculations in relativity, then it's very good, very helpful. And the third one, which I find fairly easily readable, is the one by Hans Stefani. This comes in dozens of versions. It was first written in German, then it was translated into English, and it was revamped a couple of times. So the version I've jotted down here is from 1982, General Relativity. That's also Cambridge. And this is also in German. There are also German versions. The other ones exist only in English. And this is, in my view, it's a good compromise. Between formalism and, I say interpretation, or physical understanding. So these are the three I would recommend for general participants of this course. And then I want to mention three textbooks which go deeper into the matter. There's, of course, the standard textbook on general relativity. That's the Miesner, Thorne, Wheeler. It's called Gravity. And it appeared with Freeman already in 1973, and it was never reworked. There's no more recent edition. Well, this is what we call the brickstone, or the telephone book. It's a textbook really this size of a brickstone, very, very fat, and what was relevant at this time in relativity, really everything about this you will find in this book. But I think it's only recommendable to work with this book and to go into it if you want to learn more about general relativity than just doing one course. If you really want to go deeper into the matter, then of course it's the standard book. So I write here voluminous textbook, standard textbook. Of course, in view of the experiments, it's completely outdated, right? You can imagine that since 1973, there has happened a lot on the experimental side. But the mathematical formalism, in a sense, is timeless. So this is still valid. So, by the way, John Wheeler was a person who inherited Einstein's job in Princeton. So Wheeler was a successor of Einstein. He died only recently. He was almost 100 years of age. I think he died 4 years ago or so. And the other two are former students of John Wheeler, who are now also fairly old gentlemen. Charlie Miesner was here in Bremen a couple of weeks ago when we started our Graduiertenkolleg. He gave the opening address, so he's now also one of the grand old men of relativity. And he gave a very, very entertaining talk. So that was this standard textbook, which probably is a little bit too fat for most of you. And I have two more which are a little bit more specialized. I want to recommend the one by Straumann, Norbert Straumann, Swiss physicist. It's called General Relativity and Relativistic Astrophysics. And relativistic astrophysics. That's Springer, 1984, and that's also available in German. There's also a German version. This is mathematically a little bit more challenging. So this goes much deeper into the formalism than the other ones I had mentioned. So this really gives a fairly thorough introduction into general relativity. So you learn general relativity, the mathematics of general relativity in a deeper sense than from the other books. And the same is true, maybe even in a stronger sense, for the book by Bob Wald, who is one of the leading mathematical physicists of our time, General Relativity. So that is University of Chicago Press. That's from 1984. And this is also mathematically challenging. Okay, so that's the 6 books I would like to recommend. There are many others, so maybe it's a good idea just to go to the library, look a little bit around, and to look which book you personally like, and then to use this one. As I said, when I talk about books, it's about complementary reading. So don't expect to find in any of these books the things in exactly the same way as I present them here. You'll find them in a different way, look at them from a different angle, but that's just what makes it interesting, right? So you get different point of views on these things. Okay, so the next thing I should do is I should give you a brief overview of what I'm planning in this lecture course. So I will give you a brief table of content, which is a little bit incomplete because at the moment I'm not quite sure what I will do in the last part of the term. So that's a little bit open, and I'm also open for suggestions from your side if you have a particular wish what you would like to do. But the program I would certainly want to work down is I will begin with a historic introduction. So I will present a timeline of important things which happened in the development of relativity and related subjects. Of course, it's not absolutely necessary to know something about the history of a subject if you want to understand the subject, but in my view it's always very helpful. And it gives you a deeper understanding, a better feeling for things if you can put them historically in the right place and if you know a little bit in which way they have developed. So I will spend 1.5 lectures or something like that on this introduction. I will then recap special relativity. I strongly hope that everybody in the audience has a certain basic understanding of special relativity. Otherwise, it would be really hard to grasp general relativity. Nonetheless, although I hope that everybody knows already a certain amount of things about special relativity, I will repeat this. And the reason is that I want to stress some things, some particular aspects, which will then be relevant in the following. In particular, I want to stress this viewpoint of having events, things with 4 coordinates, rather than just space, points in space, and points in time. Yeah, this idea to combine them into space-time, and then to draw space-time diagrams. This is something I want to emphasize strongly, and which I think it's a good idea to practice this in special relativity first, and then to move to general relativity. So I will spend some time with, or not too much time, of course, but a certain amount of time on special relativity. I will then do a heuristic approach. to general relativity. So if you have gained a certain understanding on, well, I should either write it always with capitals or never. So if I view it as a proper name, then I should write it in this way. Okay. Oops. So we have refreshed our knowledge of special relativity, got a pretty good understanding of special relativity, and know how to handle it mathematically. Then we will talk about how to move to general relativity. And I will do this first in this chapter in a heuristic way, so not in the sense that anything is rigorously derived in mathematical terms. It is just about physical ideas which guide us to certain hypotheses. And the most important idea which will enter into this approach will be the equivalence principle. So we will spend a lot of time on the equivalence principle, and we will discuss in some detail what can be done already with the equivalence principle alone, which is only a very small part actually of the final formalism of general relativity. And the essential thing which I hope to convey is that with the equivalence principle alone, actually you can calculate quite a lot of effect. No, not a lot, but some portion of all the effects in general relativity, actually without knowing about Einstein's field equation and all these more sophisticated things. So that will be done in this chapter. But then, sometimes we will reach the point where we really need the full formalism. So we have to talk about the mathematical formalism. So we have to talk about basic concepts from differential geometry. So we have to learn what a manifold is, what a connection is, what a curvature tensor is, and things like that. Oops. So of course I can do this only comparatively quickly because this is the subject of a 2-semester course, right? Differential geometry, if you want to do it in depth. Equipped with this formalism, we can then really develop the full apparatus of general relativity. So we can then really study the foundations of general relativity. So in particular, we will discuss Einstein's field equation in this chapter, which of course needs all this apparatus from differential geometry we have learned up to this point. And then I will discuss in great detail the most important solution of Einstein's field equation. That's the Schwarzschild solution. I will spend actually quite a lot of time on the Schwarzschild solution, because I think that's the thing where you can learn most about general relativity. So you can learn what a black hole is. A black hole is the Schwarzschild solution, which is extended to the interior as far as possible. Schwarzschild solution describes the exterior of a star, but if the star becomes too small in comparison to its mass, then it cannot stay a star. Then it has to collapse. It collapses into what we call a black hole. So the Schwarzschild solution describes regular stars, the space outside of regular star, but also a black hole, a spherically symmetric, non-rotating black hole. And we will discuss this in fairly great detail. And I will then certainly talk a little bit about gravitational waves. So that's a program which is already fixed. And probably we will have time left. Actually, I gave this course last summer for the first time, but then it was a 3-hour course. Now we have to do it 4 hours because the people from the Graduiertenkolleg have to have 4-hour courses. So that's the reason why I have to do it. Why I have to do 4 hours lectures per week this time. So I guess we will have some time left. And what I do here, actually, I don't know yet for sure. A possibility would be that we could talk about rotating black holes. That would be the Kerr solution. Another possibility would be that we talk a bit about the simplest cosmological solutions, the so-called Friedmann solutions. So at this point, I'm free to suggestion from your side if one of you wishes, or a couple of you wishes, one of them more strongly than the other things, then I could do this. So we will decide this a little bit later in the term what we actually will do. Okay, so much for the overview. And now let's begin with a historic introduction. So before general relativity came into existence, there was special relativity. And special relativity was invented in 1905 by Albert Einstein. So let's begin this timeline with 1905. Invents special relativity. Actually, he didn't call it this way. He didn't introduce the word, he didn't invent the word relativity or Relativitätstheorie. This word was coined, I think, only in 1909 or so by Max von Laue. Max von Laue called it Relativitätstheorie. And later, when two different versions of Relativitätstheorie were invented, then one distinguished special and general. So this word, special relativity, came into existence only around 1915 or so. So, but what we now call special relativity, this was invented in 1905. And what was the basic, what were the basic ingredients of special relativity? Well, special relativity is based on two postulates. The one is the postulate of special relativity, postulate of special relativity. So in German we say spezielles Relativitätsprinzip. So that's a principle that all inertial systems are at the same footing. So no inertial system is distinct. I shouldn't make such a motion. They are moving uniformly in rectilinear motion with relative to each other. So all inertial systems are at the same footing. No inertial system is distinguished from another one. And the second postulate is a postulate of the constancy of the speed of light. Speed of light. And with the help of these two principles, you can explain a lot of things, and you can understand things which before special relativity existed, people did not understand. In particular, you can explain the Michelson-Morley experiment. So if you look in a modern textbook, then you usually find a sentence of the kind, Einstein invented special relativity in order to explain the Michelson-Morley experiment. If you look into Einstein's 1905 paper, you will be very surprised because Michelson-Morley is never mentioned. It is not quoted. Actually, there's no quotation whatsoever. Yeah, it's a paper without any reference, which is really funny. Of course, it would be impossible to write something today, but at this time it was possible. So Einstein mentioned the attempts to measure the motion of the Earth relative to the ether, but he mentioned it in a general way. He doesn't refer to a particular experiment. So in particular, he doesn't quote Michelson-Morley. And when people asked Einstein, a historian asked him by letter in the early 50s, so a few years before he died, he asked him, what role in your personal development of special relativity did the Michelson-Morley experiment play? And Einstein answered, I don't even remember if at that time I had ever heard about the Michelson-Morley experiment. So what you can read in modern textbooks, that this was his main motivation for doing this, so that he was triggered by the Michelson-Morley experiment. That's certainly not true. But what is true is that this was a great achievement of special relativity, that it could explain the Michelson-Morley experiment. And what was the Michelson-Morley experiment? Hope everybody knows. So you have two light rays. So you have two light rays coming in. Nowadays the experiment is done with lasers, but at the time when it was done, it was in the 19th century. Laser didn't exist, so it was done with ordinary light. So you have a beam splitter here, and you have mirrors here. So the light rays are reflected. So one light ray goes this way, is reflected here, then comes back and is here observed on the screen. And the other light ray goes this way, is reflected at this mirror, reflected here, and then comes back. and the two light rays interfere and produce an interference pattern here on the screen. And the idea of the experiment was the following. When this experiment is done on the Earth, and the Earth is moving through the ether, then the motion relative to the ether should make one of the should make the speed of light for one of the arms different than for the other. For sake of simplicity, let's assume that the motion relative to the ether is just in the direction of one arm. Then the velocities would add. The velocity of the ether would add to the velocity of light for this here, whereas it would be unaffected for the other one. So if you now rotate the whole apparatus, then the interference figure should change. And that's what Michelson and Morley actually did. They built such a thing. Michelson first did it in Berlin, actually. He spent a couple of years in Germany, and then he went back to America, and then he repeated the experiment with great care together with Morley. And they did it in Chicago, I think, or somewhere in America anyway. And they really built a very, very high, very precise interferometer. They put it on a basin of mercury, so just to avoid all sort of percussions. And then they turned the apparatus very, very softly. Yeah? So one of them rotated the apparatus, and the other one looked into the ocular and watched what happens on the screen. And the expectation was that the interference pattern changed. Yeah, because if in the beginning the velocity relative to the ether was in this direction, and after rotation it would be in this direction. So the interference pattern should change. But what was observed was nothing changed. Although the experiment was done with very high precision, so it should be able to register even a very small velocity, much smaller than expected, even though nothing was measured. Absolutely no change of the interference pattern was to be observed. And this was a great mystery, and Einstein explained it in the simplest way possible. He explained he just said there is no ether. Yeah? Light always moves as stated in this postulate, always at this constant velocity in every inertial system. There's not a distinguished inertial system where the ether is at rest. That was the old idea, right? The ether would distinguish one reference frame in comparison to other ones. But there is no such thing. And if you accept this, which is a pure postulate, yeah, you can say, I don't like it, I don't believe in this. But if you do accept it, if you do like it, then you can immediately understand why this experiment has a null result. So this was one of the great triumphs of special relativity. Actually, what played a more important role for Einstein personally, it was not so much about explaining a particular experiment. That was a very nice and very good side effect. But what he actually wanted to do, he wanted to understand the structure of Maxwell's equation. He had found that the invariance properties of Maxwell's equations are very strange, that actually they are not understandable on the basis of Newtonian physics. So the invariance group of Newtonian physics, that's what we nowadays call the Galilei group. I think Galilei would be very surprised if you heard that such a thing is named after him, because he has never thought about things like group theory. But anyway, that's a way which is now common, so we call this now the Galileo group. That's a group which describes the invariance of Newtonian physics. And Maxwell's equations have nothing to do with this invariance group. They're invariant under a completely different group, which is called the Lorentz group. And what Einstein tried to understand is why this other group structure plays an important role in electrodynamics, but not in mechanics. And actually, he produced a new sort of mechanics, a refined sort of mechanics, which is invariant under Lorentz transformations. So the Lorentz group is a true invariance group of nature, and the Galileo group is only an approximation. It is an invariance group as long as motions take place with slow velocity. But for quick velocities, close to the velocity of light, it's no longer true. So actually, the most important achievement, I think, in Einstein's own view, was that he understands now the invariance properties of Maxwell's equation. And we will spend a little bit of time in order to write Maxwell's equations in relativistic language, in the language of 4 component quantities. And Where did I put the, here, the eraser. So that was special relativity. Special relativity, as I said, has a different invariance group from what we know from earlier physics, from Newtonian physics. So the question is, in which way do we have to modify Newtonian physics in order to fit all of physics into special relativity? And so Einstein was very successful immediately with Maxwell's equation. Actually, the whole idea came from Maxwell's theory. So Maxwell's theory fits very naturally into special relativity. It fits much better into special relativity than into anything else. But what about gravitation? So now comes the big question, how can we make a gravitational theory which actually is compatible with relativity? So obviously the old Newtonian theory of gravity is not. So we have here this speed of light playing an important role, and you certainly know that these two postulates lead to the consequence that no signal can move with a speed higher than the speed of light, that you run into logical problems if you don't accept that the speed of light has a limiting character. But you also know that Newtonian gravity has no such limiting velocity. Yeah, if you have a mass here and you shake it a little bit, then the gravitational field, according to Newton, would change there immediately. Yeah, because the gravitational potential describes something like an action at a distance. So Newtonian gravity has certainly to be modified if it's supposed to fit into special relativity. And this problem, to make a new gravitational theory that fits into relativity, that took Einstein 10 years, from 1905 to 1915, and in the end it led to general relativity. So general relativity was a relativistic theory which replaces Newtonian gravity. But this, as I said, took a couple of years. So the first important step was in 1907, when Einstein postulated the equivalence principle, which is an important step towards general relativity, but it's not the full theory, it's only part of it. So there were still 8 years to go. So what does the equivalence principle say? Very roughly, it says in a freely falling elevator, or let's say I should phrase it in the way that the word equivalence occurs. A gravitational field is equivalent to an acceleration. So I can mimic a gravitational field by an acceleration. So Einstein used to explain this with the help of this famous elevator. So if we think of ourselves being in a closed box, we cannot look outside, then we cannot distinguish the following two situations. First situation, the box is standing in a gravitational field. Here in this room, in a more or less homogeneous gravitational field, we are inside the box and we make all sorts of measurement. So that's the first situation. And the second situation is there's no gravitational field. We are away from all masses outside in the universe, somewhere in a spacecraft. But we accelerate relative to an inertial system in a certain direction. Then we have exactly the same situation inside the box. We cannot distinguish the box from the situation we had before. Yeah, the acceleration upwards has the same effect as a gravitational pull downward. They're indistinguishable. They're equivalent. That was the idea. And with this idea alone, you can calculate a couple of things. So I should write this as a first step. Oops. First step toward general relativity. It's not yet general relativity. It explains the universality of free fall, which by that time was already established experimentally very well. By that I mean that all sorts of matter fall in the same way. Yeah, if you have a stone and you have a piece of butter, they will fall in exactly the same way. Yeah, if there's no air friction. Yeah, and also this sheet of paper will fall in the same time as a stone if there's no air friction. Yeah, the fact that the piece of paper makes this sort of waving motion is just an effect of the air friction. Yeah, if you are in an evacuated space, then everybody falls exactly the same way. That's what we call universality of free fall, and that's of course an immediate consequence of this principle. Yeah, if you believe in this principle, then it must be that way, because if you accelerate the things, then of course then they will move relative to your frame in exactly the same way. Everything will move in the same way. And the third thing, it already explains, or I should say predicts, because at this time this was not measured, predicts gravitational redshift. Yeah? If you think about what happened in an accelerated system with light, if you send it in the direction of the acceleration, then you will immediately find that it is redshifted. Yeah, just as a kinematic effect of the motion. But if this equivalence holds, then there must also be a redshift in the gravitational field. So if you send a light ray upwards in a gravitational field, then it should undergo a redshift. And actually that's one thing we will calculate. Yeah, we will calculate it for a light signal which starts at the bottom of the drop tower and is sent upwards to the top of the drop tower. So we will calculate on one of the problem sheets by what amount this will be redshifted. Of course, it's a tiny amount. Yeah? The relative shift is something like 10 to the minus 14. But nonetheless, it's nowadays measurable. So that's the consequence of the equivalence principle alone. You don't need Einstein's field equation or any other sophisticated part of the formalism for this. So this was ready in 1907. So we are still 8 years away from the full formalism of general relativity. Then I should mention an important step for the mathematical formalism. In 1908, Hermann Minkowski introduced what we call the space-time, or more fully the space-time continuum. We usually just say the space-time, so that's a four-dimensional, I write the word manifold. I will explain later in more detail what a manifold is. So space is something which has 3 dimensions. Time is something which has 1 dimension. But Minkowski had the idea that one should combine these things in one entity which has 4 dimensions, which is now called the space-time. Einstein didn't like this in the beginning at all. There are quotations by him of the sort, since the mathematicians get hold of relativity, I don't understand it anymore. So he didn't like this 4-dimensional formalism in the beginning at all. But later he saw that it is the right thing to do, and then of course he used it himself very always. Yeah. Minkowski was a mathematician. Actually, he was a teacher of Einstein. When Einstein studied in Zurich at what was called the Polytechnikum at that time, that's nowadays ETH, Eidgenössische Technische Hochschule, Hermann Minkowski was one of his teachers. So he took math courses with Minkowski, and Minkowski actually didn't have a very good impression by Einstein. So he later said he was very, very surprised that Einstein became famous, because as a student he hadn't impressed him at all. And also Einstein, I think, was not very much impressed by Minkowski as a teacher. But they, when they joined forces to develop special relativity, this was very fruitful from nowadays point of view. So as I said, it lasted until 1915. Until we had the full formalism of general relativity. So Einstein finds the final formalism of general relativity. So since then, as far as the basic equations are concerned, nothing has changed. Yeah, since 1915 the theory is finished, as far as the basic equations are concerned, not as far as calculation of special effects and things like that is concerned, of course. Final formalism of general relativity. So in particular he found what is called Einstein's field equation. With the help of the field equation, he could explain immediately, he could explain one effect which was known, and he could predict another effect which was soon found experimentally, but which was at this time not known. The one which he could explain, which was already as an open problem around since quite a number of years, was the anomalous perihelion precession of Mercury. So he could explain the anomalous perihelion precession of Mercury. So in the first approximation, the planets move in ellipses, right? Everybody knows this. But if you look more closer, then you will see that actually the ellipses rotate a little bit. So the point closest to the sun, that's what we call the perihelion. This is not fixed in space. This actually moves. And you can calculate this motion and you can explain it by the perturbation of the other planets up to a remnant of 43 arcseconds. So there's only a tiny portion of the full perihelion precession. That's what we call the anomalous perihelion precession. It's not the full perihelion precession. The majority of it is just an effect of the other planets, and this was well understood since decades. But there was a remnant of 43 arcseconds, which nobody understood. And Einstein could explain it with his theory. So this anomalous 43 arcseconds per century, I should say, that's the important thing. Not per hour or per day, per century. Yeah, so the portion which could not be explained was just a progression of the perihelion of 43 arcseconds. That's a tiny angle, right, in a century. But nonetheless, this was measurable for astronomers already in the 19th century. And actually, this anomalous perihelion precession was known since, what was it, 1830-something? Yeah, 1855. And the person who found it was Hubert Le Verrier, a French astronomer. And many people had tried to explain this, and they had come up with funny theories, just in order to explain this effect. When Einstein invented general relativity, he wasn't aiming at explaining a particular effect. But when the theory was ready, he saw that he could explain this effect with this. That's, of course, much more convincing. If you make a theory in order to explain something very special, then, okay, with some effort you can do it, but probably then other things will not work nicely. But if you do a theory just on the basis of general principles, and you find you could explain it in a very natural way, an effect which was a great problem since and couldn't be clarified since many decades, and that's really a triumph for the theory, yeah? And give a very strong support for this theory, and that happened in this case here. So this convinced many people that Einstein was on the right track with his theory. And the other effect, which at that time was not measured, he predicts, with this theory, he predicts deflection of light by the sun of about 1.7 arcseconds for a light ray which just grazes the sun. So the theory predicts that if a light ray passes very closely to the sun, so that it almost grazes the surface of the sun, then according to this theory it should be deflected by an angle of 1.7 arcseconds. And this was verified in 1919 during a solar eclipse. By Sir Arthur Eddington and 3 other team members. And this was a great triumph for Einstein, of course, that what he predicted was actually measured. And this was the time when Einstein's world famousness started. To this point, he was known to experts. Immediately after 1905, he was a very well-known physicist among experts. I think he was suggested for the Nobel Prize for the first time in 1908. He got it in 22 then finally. So he was very well established in the physicist community since 1905. But not for a broader audience. If you ask a man on the street, he had never heard about Einstein. And this changed in 1919. Then all the newspapers, the ordinary newspapers, reported on this expedition, and the American tourists came into the lectures by Einstein in Berlin. So just to watch this famous person. Yeah, so he was really a celebrity since 1919. Okay, so these are the 3 famous effects predicted by general relativity. The gravitational redshift, we will talk about this later in great detail, which actually only needs the equivalence principle, and then the anomalous perihelion precession of Mercury and the deflection of light by the sun. That's what is called the classical effects, the 3 classical effects. And of course, we will derive them, the mathematical formulation of them in great detail later. Also 1915, immediately after Einstein's field equation was established, the first non-trivial solution to it was found, and actually a solution which up to now remains one of the most important solutions, arguably the most important solution. That was found by Karl Schwarzschild. Finds the spherically symmetric and static solution. It's really the, because it's unique. Yeah, it is the spherically symmetric and static solution to Einstein's vacuum equation, vacuum field equation. And that's what we nowadays call the Schwarzschild solution. Actually, Schwarzschild worked on this. Look, 15, this was in the middle of World War I, right? Schwarzschild was at the Russian front. He was German, of course, and he was with the German army at the Russian front, and he caught a very bad skin disease, which leads to it is called Blasenfieber in German. I don't know what the English name is. So you get blisters on the skin, very ugly and very painful blisters. And actually, he died from this disease. He died a few months after he had established this solution. This was work he had done at the Russian front, and then he came back, and a few months later he died. So he had just time to send it to Einstein. He submitted it to the academy. This paper to Einstein. He submitted it to the to the Prussian Academy of Science. And of course, Einstein was enthused by the fact that somebody had found an exact solution to his equation, which to him seemed so complicated that he actually had no hope that in a reasonable amount of time anybody would come up with an exact solution. So Einstein was very happy about this, and immediately after this paper was finished, Schwarzschild then died at the age of 40-something. So this was the Schwarzschild solution, which describes the space outside of a spherically symmetric mass. So this could be a star, or it could be something else. And actually there's a hint that it describes also something else than regular stars, namely the Schwarzschild solution displays something which was later recognized as a coordinate singularity. So it's a sort of singularity, but actually it's a singularity which can be removed by making a coordinate transformation. This was not understood for many years, and the singularities appears at the so-called Schwarzschild radius. And the Schwarzschild radius, usually abbreviated RS, is given by 2g m over c squared. So what are the quantities? G is the gravitational constant. C is a vacuum speed of light. And m is the mass of the spherically symmetric body. So in this solution, there appears a singularity. So if the radius coordinate takes this value, then you get a 0 in the denominator, which is always bad, as you know. And people didn't understand what this means. Of course, if you calculate the numerical value of this thing for ordinary stars, for instance, for the sun, if you insert here the mass of the sun, you will find that this is just 3 kilometers. So this is, of course, tiny in comparison to the radius of the sun. And the solution only holds outside of the body. So outside of the body, of course, the radius coordinate doesn't take this value. So people said, okay, for ordinary stars, this is irrelevant. But the question is, what happens if you compress the body below its Schwarzschild radius? Yeah? If you take the sun, at least in your mind you could do this, and compress the mass to a radius of less than 3 kilometers, then the singularity would be displayed. And the question is, what happens then? You have a 0 in the denominator. What does this mean? What goes wrong? And this was not understood for decades. It was not understood during Einstein's whole lifetime. He died in 1955, and he never understood what happens at RS. It was understood only in the late 50s. And the person who explained it was David Finkelstein, and he realized that what happens here is that you have a horizon. Yeah? So, and what forms, if you compress the body under its Schwarzschild radius, that's what we now call a black hole. So a black hole will be formed. It has a horizon at a certain radius value, and that's what we know now. But that's something which we learned only many, many years after Schwarzschild. So we will talk about this in great detail. So at this time, this was really a riddle. Nobody understood what was going on at this particular radius value. So this was one important success of Einstein's theory, that one could find an exact solution which describes spherically symmetric bodies. And you could study all the effects which follow from general relativity in terms of exact equations. So no approximation was necessary as long as you accept these idealizing assumptions, that the body is perfectly spherically symmetric and that it is static. So this was a contribution by Schwarzschild. Einstein himself drew another very important consequence from his equations. This was a little later, 1916. He predicts the existence of gravitational waves. So he looked at his equations and he saw that, at least in some approximational sense, they would admit wave-like solutions. Solutions and exact solutions, which have a wave-like character, were found only much later. But approximate solutions, solutions which were found as solutions to an approximation of Einstein's field equation, were found by him in 1916. So this was on the basis of an approximation of Einstein's field equation, and the approximation was in the fact that he linearized the equation on the basis of the linearized Einstein equations. So this was a theoretical prediction, and if these waves exist in nature, this is an open question until now. So they have not been directly discovered. They have been, in a sense, indirectly discovered. So one has observed a binary star system which loses energy. So what you observe is a loss of energy, and the explanation is that this energy is radiated away in terms of gravitational waves. But the waves itself have not been detected until now. So that you have a detector, and the detector makes click and tells you there's a gravitational wave run through it. An experiment of this type has not been done until now. There are many gravitational wave detectors who try to do this, but there was no success until now. So this was about more or less local solutions. So here you describe stars. You have the space-time in a neighborhood of a star, and here you describe wave-like solutions which also move only in a restricted part of the universe. Einstein also asked about cosmological solutions, models which describe the whole universe. And he found that his equations have a feature which he didn't like. Namely, they had the feature that this global cosmological solution had a strong tendency to be time-dependent. He worked really hard to get something which was not time-dependent, which was static. At that time, like most other people, Einstein thought that the universe should be time-independent. It shouldn't change in the course of time. He wanted to have a time-independent model. And because his original equations didn't like solutions of this sort, he modified his equations. So he introduced, this was in 1917, he modifies his field equations by introducing what is now called the cosmological constant. With this modified equation, he was able to find time-independent solution. So this allows to find time-independent, that's static as we usually say, cosmological solutions. And Einstein was happy about this because he wanted to have a time-independent solution. Nowadays, we are pretty much convinced that our universe is not time-independent, that it actually is expanding. But that was an idea which came up only later. And this original motivation for introducing the cosmological constant is now gone, of course. So nowadays, we wouldn't need it in order to get cosmological solutions which are in agreement with observations. But nonetheless, the cosmological constant is still around, and actually the majority of people think that it does exist in nature and that it is different from zero, and it still plays an important role in modern cosmology. And we will talk about it a little later. But the original motivation was something which is now obsolete, of course. Yeah, another thing I should mention is in 1918, there was a famous paper by two people who are usually awfully mispronounced. Actually, one was Austrian, one was Bavarian, so the pronunciation should be German. The pronunciation is Lense-Thirring. You usually hear them pronounced, even by German people, you hear them pronounced as Lenz-Thirring, which is absolute nonsense. So the name were Joseph Lense and Hans Thirring. Find theoretically an effect which is now called the Lense-Thirring effect of rotation of the source on a gravitational field. So that's something which is completely new in comparison to Newton, gravitational field. In Newtonian theory, if you have a star, it has its gravitational field around it. It's given by the gravitational potential. Now, if the star rotates, it has precisely the same potential outside. Yeah? As long as it is homogeneous and so there's no wobbling or things like that. As long as it is spherically symmetric, homogeneous, then it doesn't matter if it rotates or does not rotate. It has precisely the same field outside. But in relativity, that's different. So the rotation, so to speak, gives an additional contribution to the source of the gravitational field. It produces additional gravitation. And that's what we call the Lense-Thirring effect. Yeah, let me write this here. And this is something which is, only to a not quite satisfactory amount now verified by experiment. It is to a certain degree verified by experiment, but not with the accuracy we actually would like to have. So that's a very, very typical relativistic effect, which exists only in relativity. And as I said already, 1919, this was a famous year with a solar eclipse. So Arthur Eddington verifies Einstein's light deflection formula. I've mentioned this already. Then for many years, actually, the formalism developed only in the realm of cosmology. So as far as stars, description of stars or wave-like solutions are concerned, there was not much progress in the 20s and in the 30s. The progress was in cosmology, in particular by the Russian mathematician Alexander Friedmann. This began in 1922. Actually, it was a series of papers over 2 or 3 years. Alexander Friedmann, that was a Russian mathematician. Actually, he wrote German, so the papers are written in German. He finds expanding cosmological solutions. And he takes them seriously. So these are the ones which Einstein discarded. So he said, that's not what describes nature properly. But Friedmann really takes it seriously and works them out in great detail, expanding cosmological solutions of Einstein's field equation. And they are called the Friedmann solutions. And well, if we have time enough, maybe I could talk about them at the end of the course a little bit. So now the idea was around that actually the universe is not time independent. It actually changes over time. And when one studies these solutions in more detail, one finds that actually they change in time in a quite dramatic way. Namely, at some particular time, they have a strong tendency to develop a singularity. So a large class of these solutions, a large class of these time-dependent expanding solutions actually start from a singularity. So they start from a point in time where the whole universe was condensed in one point. And the person who just investigated this cosmology first in detail, this cosmological singularity first in detail, and took it seriously and said this could be a realistic model of our universe, was Georges Lemaitre. This was in 1927. Lemaitre studies what we call the cosmological singularity. And I think everyone knows it better under the funny name, which was actually introduced, ironically, Big Bang. Yes, this word Big Bang, this was originally meant ironically by Fred Hoyle. who was a great opposer of Big Bang theory. Yeah, he thought this was absolutely ridiculous, the idea that the universe started with such a thing, and he called this Big Bang, and what a funny idea. And he didn't understand that this actually became a term in the scientific literature. Yeah? The word which he had meant to ridicule the whole theory, this is now used as a technical term in the theory. This was in the 60s. So the father of Big Bang theory was Lemaitre in 27. It was on the basis of Einstein's field equation. Yeah? So he came to this idea by studying solutions to Einstein's field equation. So Lemaitre was the first who took this really seriously, so I think it's fair to call him the father of Big Bang theory. And then it was studied in great detail by Georgi Gamow, for instance, and others. So this was, from the theoretical side, an important step in cosmology. And there was also, from the observational side, an important progress. In 1929, this was by Edwin Hubble. So this was the first experimental or observational hint in the direction that this idea of an expanding universe could be the right idea. Yeah, it was introduced on purely formal grounds, just by studying a mathematical equation somebody had come up with. And Hubble found experimental or observational evidence for the theory, but let's be careful. What he found exactly was a linear relation between the redshift and the distance of galaxies. That means the farther the galaxies are away, the stronger are the lines in the spectrum redshifted and distance of galaxies. So this is just an observational fact. This alone is not directly related to the idea of an expanding universe, but if you interpret the redshift as a Doppler effect, you say this redshift comes about by the fact that these galaxies move away from us. You all know the Doppler effect, right? If a source is moving away from you, then you see it redshifted. Or for sound waves, you see it shifted in the direction of the longer waves. So the sound becomes deeper. So that's, if you interpret the redshift in this way, then you come to the conclusion that the farther things are away, the faster the move away from us. So the whole universe expands. So that's so this will be interpreted as expansion, as Doppler effect, showing an expansion of the universe. Actually, Hubble was fairly careful. If you look at his paper, he doesn't say, I have detected that the universe expands. He's just speaking about this linear relation between these two observational things. So the interpretation is up to you, but most people read it in this way. So I think it's fair to say that Hubble was the one who found experimental evidence or observational evidence for the expansion of the universe. He was the first to find this. Okay, the next things on my list are also related to cosmology. You know that the idea of dark matter is now around. It's now very fashionable. And many people have the idea that this is a recent idea, that this came up only recently. Actually, the idea of dark matter is very old. It was introduced in the 1930s. And it was introduced in connection with these cosmological ideas. The person who came up with the idea of dark matter first was Fritz Zwicky. It was in the 30s. 34. 1934. Fritz Zwicky, a Swiss-born astronomer who lived in the United States. So he postulates dark matter. And the reason why he did this was that he found that without dark matter, he couldn't explain the stability of galaxy clusters. So there was not enough matter in the galaxy clusters in order to make the thing stable. So they should fly apart. Gravity wouldn't be strong enough in order to keep them stable. to keep them together. He had to introduce dark matter in order to bring the observations in agreement with theoretical explanations. So actually they would fly apart fairly quickly. Yeah, so in a time that this would really be in disagreement with observable facts. So he postulates dark matter in order to explain stability of galaxy clusters. And nowadays we are fairly convinced that there's a lot of dark matter around, and we need this in order to make cosmological models, to bring it into agreement with modern day observations. So actually, if you stick to Einstein's theory, if you don't want to do a more complicated sort of theory, then you have to believe in dark matter. You have to assume that there's dark matter around. Matter which we don't see, which is not emitting light, which is only observable to us by way of its gravitational field. And at about the same time, Zwicky made another important contribution. Or actually, he started another important development. This is related to the light deflection. We have talked about the light deflection near the surface of the sun. Now imagine a gravitational field produced by a stronger object, by an object which is more compact or has a higher mass. Then the deflection angle would be much bigger. This tiny angle of 1.7 arc seconds is related to the fact that the sun is comparatively light. It has a comparatively small mass in comparison to its radius. If we have a much more compact object, then this deflection angle could be much bigger. And this could lead to double images. Yeah, it could lead to the effect that from a light source, one light ray goes this way, another light ray goes this way around the source, and I see two images of one and the same source. This idea was around since the 1920s. Actually, it's found in Einstein's notebook already from 1911 or something like that. So he had thought about this possibility very early. But Zwicky was the first who really went to the telescope and looked into the sky and searched for such double images. So he started search for double images. Produced by relativistic light diffraction. So this effect is now called the gravitational lens effect. He never found anything. He really observed for years and years. So he continued into the 1950s. But he never found anything. He died around 1970. This was 9 years before the first double quasar was found. So his search was always without success. Okay, I think time is over. So I will have to continue with this timeline a little bit more, maybe for half an hour or so. And then we can move on to special relativity and begin a little bit to draw space-time diagrams and to discuss the geometrical aspects of the theory. So I will send an email message to everybody around. Here's a list. Everybody is now on this list. Everybody who wants to be informed about what's going on. Good. So I will send, can I read this? Let me check this. Yeah, I think with some effort I can read this. Yeah, okay, good. So I will then send you a message and we'll meet at Friday at 4. But I also have to check with you if you could come. I think if this is not possible for you, then we would have to do something else because it should be recorded for the people in Bielefeld and Oldenburg, right? So we have to check over the. So by what time would you know if you would be available Friday at 4?
I can tell you tomorrow early home class.
Okay, fine. And then we have. Okay, and if this works out, then we will meet Friday at 4 somewhere. Okay, see you then.